Vooraleer we de doctoraatsverdediging in het Engels laten plaatsvinden, wil ik graag eerst even in het Nederlands de kandidaat voorstellen. Ik denk niet dat dat echt nodig is, maar ik ga het toch doen. Timothy Cameraman werd geboren op 5 juli 93 in Kortrijk. Hij ging ver weg studeren in Campus de Naaier, waar hij in 2016 zijn masterdiploma haalde. En zijn masterthesis deed hij in de groep van professor Goedemee bij Inge Coudron, waar we die onlangs nog haar doctoraat verdedigde. Ik was ook aanwezig in die doctoraatsverdediging. En in deze thesis nam hij zijn eerste stappen in het veld van AR en alles wat te maken heeft met machine learning en dat soort dingen. En dat intrigeerde hem en dat zette hem aan om daar iets meer over te weten te komen. En hij startte dan ook als wetenschappelijk medewerker bij professor Goedemee in het kader van het project rond het bouwen van een autonome cameraman. En in 2017, een jaartje later, dan startte hij zijn doctoraat, dat hij vandaag dan in openbare zitting zal verdedigen. Mr. Cameraman has submitted a PhD thesis to the Faculty of Engineering Technology of the KU Leuven on the topic of scene perception, generating and exploiting vision-based metadata, in partial fulfillment of the requirements for the degree of Doctor of Engineering Technology. He will now publicly defend his PhD thesis. Mr. Cameraman, may I invite you to give a presentation of about 45 minutes about your work, and then afterwards the examination committee will have the opportunity for discussion and questions. You have the floor.
Thank you, Chairman. So welcome everybody. I hope the microphone is fine. Okay. First of all, I want to thank you for coming, and also note that there are live subtitles at the bottom for non-English speakers. Note that this is live and automated, so prone for error. I've not written this, so if there's some funny content coming up, please excuse me or the AI. Okay, so my public PhD defense today will be titled Scene Perception, Generating and Exploiting Vision-Based Metadata. And first I will start with an outline of what I will be presenting today. The first thing will be my background, followed by the use cases, lessons learned, and then my conclusion. And in this background I will provide you with some information that will help you in this journey of my PhD to understand it some better. So first, when we take a look at my title, then you can actually extract certain things from that title alone. And the first thing you can extract is the name scene perception and vision-based. So everything within this PhD has to do with something vision-based, and we try to perceive what is happening on those camera images that we capture. Then we will generate metadata based on that vision data. This can be the position of people or the skeleton of a person, in which I will go to in more detail later. And then we will also try to exploit this data to do something useful in the industry, like directing or steering a camera or counting the number of people present. And nowadays, cameras are everywhere. So when you look around, probably you don't notice them anymore because you are so used to them. And this was not always the case. When we take a little look back at the present and compared to the past, we can actually see that cameras are relatively new, only 200 years old, but nowadays almost everybody has one in their pocket. A smartphone with a camera is not unique anymore, and at least somebody has already seen such a device. These cameras today are very cheap, small, offer great image quality opposed to the past cameras, and are therefore used in various applications. Some examples can be seen at the right side of the slide. And when we take a look at this map, I don't know if somebody recognizes the place, but this is London, then we can actually see that there are a lot of cameras present in London alone. And if you take the time to count each and every one of them, then you will come up to the number 911 CCTV cameras who are currently present today in London, probably some more since yesterday, And you can ask yourself the question, who is watching all these cameras? This is an immense task with a lot of labor which comes in it. And part of this slides will show you some methods how you can maybe make a computer do some part of that work in watching those cameras. So take that with you along the journey. Then a little bit more details about, what is that camera? When we look at that smartphone, then a camera actually has several components, but the three basic or most necessary components are a lens, some filters for color filtering, and eventually a light-sensitive sensor. And light will actually be captured on that sensor, filtered in RGB, red, green, blue, and then we can actually see that there are some complex algorithms which will actually represent an image in 3 color channels. Okay, so why is this important? Well, when we take a look at this image, and I pose you the question, where is the green apple? Then you can only take a guess at which of these 3 apples is actually the green one opposed to the 4 red ones. But when we use the 3 color channels, then probably red and green, since those are one of the channels, probably those channels will help you in finding the right apple. And when we look at the red channel, where the white pixels, the whiter the pixel, the more red the color contains, the blacker the pixels, the less the channel is actually filled, then we see that in the red channel, the green apple does not appear very clearly. Okay, well, we continue, and in the green channel, we can actually see that 1 apple stands out. So apparently one of the 5 apples does contain some green pixels opposed to the other ones. And then for completion, we also show the blue channel, and of course there is no blue, but you can guess that indeed the center apple is the green apple. So the green pixels can actually be used as a type of simple object feature to describe a certain parameter or certain attribute of an object. And suppose we have bounding boxes around our object, around our apples, then we can actually use that visual color information to classify whether it's a green or a red apple. So it's important that we know that there are features and that it's basically just a bunch of numbers which together give us some more metadata, some actual attributes behind them. And in most cases we have classification, which is describing which class the object or something is. So like example, the green apple is mostly green and the red apple is mostly red. But in some cases, unseen or untrained data, like a yellow apple, might cause some confusion. So most of the objects must be known before they can be classified, which is pretty obvious. And then we have detection, which gives us more information, like bounding boxes around the objects represented by an X, Y, width and height component. And when we think back of my London example, then we can already maybe have some answers based on my Apple example alone. Suppose we have a detector for faces and a classifier for wearing a mask or not wearing a mask. Then you can imagine that for the 911 cameras, we can already fix some watching element of those cameras. However, an apple is not the same as a face. It's a lot more difficult to detect or classify a face opposed to just a green or a red apple. And therefore, we actually took a look at how humans learn how to detect or find people or objects in general. And we actually proposed to use AI models in which we feed a lot of examples, and then we let a model train by example to eventually let it do a task, in this case, the task of detecting or finding the face in an image. And these techniques, these AI models also had some history, and certain techniques have been around since 2001 and are still evolving. And since 2012, the major category of techniques are formed under the convolutional neural networks, which are rising in popularity or have risen a lot, and are also used within this PhD throughout my work. Well, a little bit more detail about how convolutional neural networks work. Well, if we want to classify a handwritten digit, then we can take that digit, we can extract it in a one-dimensional matrix, We feed it to a network that we proposed, and then we can let it go through certain hidden layers. And based on the examples, and we continue to say this is 9, try to find something unique to the number 9, then we can hope that in the first hidden layer it will find certain fragments of the number 9, and in the later hidden layer it will have a more high level representation, the 0 and the 1 or the stripe, and then at the end it will eventually classify it as this is number 9. So convolutional neural networks have a similar behavior where we try to have indeed more complex networks than just 2 layers, but it works the same way where we have certain hidden layers which we train to have a certain behavior, and we train them by example. And within this PhD, 3 types of detectors or metadata extractors were actually used a lot. We have the YOLO version 2, which is an object detector, not only providing us with bounding boxes around the objects, but also the class. We have an open pose framework or a key point detector or a pose estimator in general, which tries to find the key poses or the key points of a person. And we also have YOLACT++, which not only wants to show us the bounding box around the person, but also the pixels which depict that object, or in this case, persons in the image. Now, when we look at how these techniques are evaluated, because we can now see a pretty picture showing us already some cool graphics, but in general or in research, we also have to try to evaluate how these techniques work. And when we have this example, then suppose we have a face, the model, which is capable of finding the faces, and we run it on this image, then we can see that certain faces are found. In this case, we also need annotations. Annotations are regions where humans have said this is the area of a face. And using these two components, we can actually already extract certain elements of that image. We can count the false negatives, as you can see at the top center. These are detections which should be detected but are missing. We have true positives, the face of the father at the right, which has an annotation and a detection. So this is the ideal case. And then we have false positives at the bottom right and bottom left, which are detected faces but shouldn't actually be detected faces. And when we use these 3 metrics, we can actually calculate how precise and how our recall is in our model. Precision is showing us how good our detections are actually showing up. And recall shows you how many of the detections we actually found or lost or didn't find. And when we count and we use this math to calculate the precision and the recall, we can see that we have at a confidence of 0, so no thresholds, we can have a precision of 75% and a recall of 75%. And we can raise the threshold a bit, then certain detections will fall off. And then this will cause us to rise in the precision, since the one detection at the bottom right has disappeared, but the recall stays the same because we don't find any more faces. The people at the middle center are not found by raising the threshold. And we can raise this even further, causing us to have 100 precision, but only a recall of 50. This means that all our detections are actual faces, however, only 50% of the faces are found. And we could continue further and further, but then we have a long table. Instead, what we often use is a PR curve or a precision recall curve, which actually shows us the progress of our threshold and the influence of that on the precision and the recall. And to compare techniques in papers and publications, we actually don't use these curves because it's very tricky to compare fairly how well something works. We actually extract the average precision, which is the area under the curve, and that gives you a single number which you can use to compare yourself with other techniques. So this is how most, or at least object detectors, are used or are evaluated when they are researched. However, what if we go to another field? What if we go further than just bounding boxes and we go to a field of directing a camera to take certain positions inside of a frame? Then it's not very clear what an annotation should be, and because it's live, it's happening right now, and it's not always possible to have the ground truth which we need to compare our outputs. So what about performances of these real-life industrial use cases? How can we actually also have a metric or compare themselves in these cases where it's not so trivial to find human annotations? So the research question within my work here mainly comes up to this question of what performances can we expect from people-based scene perception techniques in real-life industrial applications. Well, we ask ourselves, can current techniques provide us with fast and accurate metadata, and can the extracted metadata be used in real-life industrial applications? So this was a little bit of background. I hope you have some baggage to go further into this journey, because now I will discuss my use cases, which I used as real-life use cases within this research, to see whether or not certain techniques are indeed valuable or usable within this research. And the 4 cases that I will be presenting today are the autonomous cameraman, mobile eye tracking data analysis, privacy-aware people counting, and people-based 3D maps, occupancy maps. The first one will be the autonomous cameraman. A while ago, since, as the chair said, it was my first research project, then a camera crew or a production house actually came up with the idea of, well, suppose we have a household and we actually want to record what's happening inside of that household. We want to record a reality show where people are just doing their daily tasks and daily lives, and we want to record what's happening there to see whether or not it's an interesting production or an interesting TV show to put on the television. And they placed pan-tilt zoom cameras, which are movable cameras, inside of the household, and to have some assistance, they also provided overview cameras. So when they zoom in on a certain person inside of the room, then they still have an overview of the complete room to adjust their shots if needed. Well, they used this overview camera to steer the pan-tilt zoom camera, and on their pilot, they were actually looking at how will we do this. And this is the typical view of a person that is working there in the company. And okay, he sees the cameras and he's tasked with controlling the cameras. And then he's also tasked with recording the cameras, because recording it full time when nobody is present, that would be useless. And as well, taking notes, because when you record over certain months, then nobody's going to remember what's happened, and then notes can help you with some guidance in the footage that has been recorded. And then they were calculating, well, we have 8 cameras for a single household, and our ambitions are to record 3 households simultaneously. That means 8 times 3, that's 24 cameras that I have to control, record, and take notes of. And then this has to happen 24/7, because our daily lives probably vary from the ones in the households. So we cannot expect them to be there when our working hours are currently present. So somebody has to sit there 24/7 controlling 24 cameras. As you can expect, this is a very tiresome task. Remember the London case, 911 cameras. So they wanted to automate this. And within this project, our goal is to actually trigger recordings based on people activity or people presence. We want to steer the pan-tilt zoom cameras to take cinematographically pleasing medium shots. We want to have an objective study of the shot quality. And as well, we want to generate timetables based on actions, people, and locations, and sound labels within the scenes of the recorded footage. And to do so, we proposed an approach to add some blocks to our pan-tilt zoom camera and our overview camera, where we use the bottom part, the overview camera, to steer the pan-tilt zoom. First, we take the overview camera image, which we feed to an activity detector. This activity detector image afterwards will also be fed to the pose estimation network, which I will discuss further in the presentation. And then based on the poses, we will actually calculate a position for the camera, a desired position. Both the activity detection and the medium shot calculations get sent to the pan-tilt zoom camera. The activity detector will actually trigger recording, and our medium shot calculator will actually position our camera. And then the camera images, which are recorded and positioned, will actually be run through an action recognitioner, a sound recognitioner, and a face recognitioner to generate the event timelines over time. And some of the parts have been done by me, which I will discuss later, and this was also work with other colleagues. So certain parts will not be discussed by me, the top right parts. But the first part is the trigger recording. So we want to trigger recordings based on people activity before they actually move from one room to the other room. And how we did this is that we actually divided the rooms up into several zones, and we attach a bucket to each zone. And here you can see we have, to the left, we have a yellow bucket for the hallway, a blue bucket for the living room, and a purple bucket for the kitchen. And the overview cameras, when we are present inside of the image of the overview cameras, which overlap with the doors that divide the rooms, then we can actually fill some activity inside of the bucket. And at some point, the bucket will get full enough to trigger the recordings. And in this case, our hallway camera 4 is being triggered to record. However, when we move from the hallway to the living room, just before we open the door, then we are actually active or visible on multiple views, also on camera 1 and 2, because the door is already moving. Then more activity will get inside of the bucket of the living room, causing the cameras of 1, 2, and 3 to be triggered and to record. And this means that before we actually move to the other room, the cameras get recorded. And when we look at the results, we can see that we significantly reduced the recorded footage and also the editor search space, so the footage that has to be searched to afterwards. We have 0 false negatives at the compensation of having certain limited false positives, which means that we sometimes start too soon and sometimes record a bit longer than should be. And in the bottom right, you can see an example of the system working. Okay, so now we can trigger the recordings. Then we only need to steer the camera to a certain spot to take medium shots. And a medium shot, if you have 2 people present looking to the right, then a medium shot is described by the cinematographic world as a grid which shows us the bottom of our stomach and just a bit above our head. And then we position the people on the lines, the vertical lines, to give a cinematographically pleasing shot. We cut it out, or at least the PTZ will zoom in, and this will be the shot that we are trying to achieve. And at first what we did is, since it's using the upper body of a person as a reference, well, why don't we train a traditional technique to detect where the upper body of the people are? And in this case, we used an upper body deformable parts model, which indeed caused some detections to occur. And based on the detections and also a face detector, we can actually estimate where our grids should be placed. And when we look at the results, we can indeed see that our detections are fairly acceptable in ideal situations. Also in time, it's capable of directing the camera without missing or without the people leaving before you actually steer the camera. However, certain limitations are set inside of this solution or approach. We only evaluate the upper body trained models. Remember that I said we only have our ideal annotations which we use as an evaluation, which is not fair because the actual shot quality is not measured yet. And we only have a limited subjective evaluation of the actual shots. Namely, we sat down with the production crew and they said, could be better. So we listened and we actually worked on a version 2.0, and we actually used an open pose, so the network that I talked before, which you can see to the right, which will try to classify each point of our body, so our elbows, our shoulders, our wrists, etc. And then it will try to combine them by also trying to find part affinity fields. These are connections between certain body parts, and together they will estimate the full body pose of people present on the image. And the network representation you can see at the bottom right. And this means that we have, of the 2 characters now, more information. We don't have the grid around the upper body of the people, but we actually have the key points of that person. And that means that we can actually estimate not one, but several of these grids, and we will try to minimize the size of that grid to get a full or a better, clear, zoomed in version of that grid. And then we can select a single minimized grid or medium shot to be steered to the camera. And we also listened at their method of evaluation, and we also created a framework or an application in which they are actually capable of very quickly evaluating how well our model is actually performing. So we show them some shots which we propose, and then they get the chance to evaluate it using some smiley faces, and then they get also the chance to steer the camera to what they actually would provide us as an ideal situation. And the results actually show, to the right in the table, that we are already capable of steering the camera to an acceptable amateur level of cameraman. However, there is still some room for improvement to get to the professional level. However, this is already acceptable for the camera crew. So our contributions here is that we are the first to propose such an approach to are capable of automatically steering the camera towards medium shots complying to cinematographic rules. And we also generate timelines combining multiple audiovisual recognition techniques, which was mostly the work of colleagues of mine. Our metadata extraction is in the wild household footage, so which is challenging data, taken from multiple cameras in various point of views. And we want to exploit it by taking cinematographically pleasing medium shots, also triggering pre-rolled recordings and having an overall footage analysis. And 2 publications were derived from this work. Okay, this was the first use case. The next use case is titled Mobile Eye Tracking Data Analysis. And this is a different approach. We're leaving the field of the cinematographic world, and we're actually going to the people science. We're going to how people actually conversate with each other, and apparently some research groups are actually interested in how well or where we are looking at what point in time. So during a conversation, are we looking at the faces, or some people tend to look more at the hands or next to the faces. And this tells something about the conversation and also how well that conversation was perceived. And how they actually do this is, well, they are mainly interested in the face region or the head region and the hand regions, because the presumption is that most of our attention goes to that during conversations. Currently, they use a mobile eye tracker, which is a kind of smart glasses, as you can see here, which is mounted with a frontal-facing camera, capturing our field of view, as the wearer of the glasses would actually perceive. And there are also 4 eye-faced cameras which actually capture where we are looking at. And based on both, we can actually plot on our perceived field of view where our gaze, our eye gaze, is currently directed at. And the data which is recorded from this mobile eye tracking experiments is actually, in most cases, done by students. Most of the time they want to, in ideal situations, record a lot of data, and then over the summer holidays they try to find 2 students who have still 50 work days each available, and then they have 40 hours of data which have to be annotated by those students. And roughly measured, we actually need 1 hour of annotating for 15 minutes of footage. This means that they actually need 160 hours to annotate the full data set. And only 8, legally in Belgium at least, only 8 working hours can be filled in a student's workday. This means that they have 400 hours together to have annotations. And this means that this allows for 4 annotations of the data. Take in account that students also have some work ethics which might vary, and annotating 8 hours a day for 50 days in a straight line over the summer holidays, this is not very ideal. I've been a student myself and I've done more fun work. So I can imagine that they also wanted to have some automation happening here to also relieve the students of the boring work, but also have maybe more qualitative and faster results. And to do so in this use case, we actually compared between detection models using a person pose detector, which I discussed already a bit before, We also want to train a head and hand object detector, specifically for certain regions in which the researchers are interested in. We also want to imitate the human annotator's preference, because our opinion of when you are looking at a head region might vary from the researcher's opinion, because there is some error margins in the glasses as well. So we want to see what the preferences are in the human annotator. And we want to measure the performance for automatic mobile eye tracking data analysis using different annotational shapes, multiple person identities, and various movement levels. Our approach that we followed is, well, we have the YOLO version 2 network, which is trained using the COCO object dataset, and it's trained to detect 80 objects currently. However, we don't need 80 objects, we only need our head region and our hand region. And in the COCO dataset, one of the objects that is present is a person. So think back of my example, there are some hidden layers inside of that network which know how to describe a person in full, which means that hands and a head should also be part of that network or those layers. And what we can actually do is we can actually fine-tune or redirect this model to not detect 80 objects, but only the specific objects which we want to train the network for. And we can do this by deleting the last piece of the model, and then we can actually fill in a new layer at the end with the number of classes that we need, following the architectural needs as well. And then we can feed data to that network using pre-trained weights, the weights that were already there on the COCO dataset. And we train data, or we train further using head regions and hand regions to have a new layer at the end capable of detecting hands and head regions. And when we do this, we actually see that indeed it is possible to detect it with a certain confidence visually, and later I will show you the results more detailed. In the next approach, the second method, we actually want to use the same pose, which gives us already certain aspects of a person. It gives you the key points, and therefore you can also calculate certain areas. However, the area of the region does not come out, which means that we actually have to extract or use these key points to determine what the head regions and the hand regions are. And for the head regions, we actually use the key points on the face, which are the ears, the eyes, and the nose. And we calculate the width and the height using an aspect ratio and a margin, which can be enlarged based on the preference of the human annotator. Both frontal and profile models are trained or are used for parameters, because this varies a little bit. When you go sideways, the regions get smaller. Then for the hands, we can actually use OpenPose to extract also the key points of each individual key point in our hands. And we can actually draw a bounding box around them to describe the region of the hands. We can also use the elbow and the wrist position to estimate a region where our hands should be. And this means that, like you can see in the example, when our hands are actually not visible, then based on that semantic information, we can also determine our hands should be somewhere in that region, which might get useful. Visually, both of them present very good results, work fast enough, and actually show that it's in the very motile images, which are sometimes blurry, it shows something that is reliable already. However, when we look at those precision recall curves, the recall is in the horizontal, the x-axis, and the precision in the y-axis, then we can actually see, I hope the figure is clearly enough, but we have the blue line in the left-hand figure, which is the OpenPose-based technique, which reaches a larger recall. It goes further in recall, and this means that we miss less faces. So in all of our video, we actually have more faces that we recognize, while YOLO drops at a certain point, meaning that certain faces get dropped inside of the data. For the hands, a similar behavior. On the left side, we have an easy data set. On the right side, we have a more difficult or challenging data set. We can see that OpenPose has the same behavior of retaining its recall to a higher point, while YOLO at some point breaks off and loses the hands in the images. So in our continuation, we actually prefer OpenPose because most of the times they still perceive the hands and the head regions independently of what is happening or more detailed. At the end, we also created a tool for colleagues in the UMC in Amsterdam, Chiara Jongerius, in which together we in cooperation made a publication and also an application which they can actually use extracted open post data. They can import it in a program as well as the video and the case data. And they can actually also add identities inside of this program. For example, for herself, the researcher, they can appoint a certain bounding box as that identity. And for the continuation, frame by frame in this video, it will actually try to match that certain region based on that identity that was pre-known. And in her research, or in our research, we actually evaluated this approach or this method fully, end to end, showing that indeed our approach is comparable to a human annotator with a small error margin. So in larger sequences, we can see that the error is enlarged, but this might also be an error in the human annotations as well. So it's an acceptable rate with Cohen kappas above 0.85% or 0.85, and re-ID accuracies well above the 95%, which is already quite acceptable. Our contributions here is that we have a state-of-the-art autonomously annotating tool for mobile eye tracking data, which is capable of frame-by-frame person identity detection and also body regions that can be extracted on very motile video. And we are also capable of imitating annotational preferences from human annotators. Also, 2 publications were derived of this use case. Our next use case is that of the privacy-aware people counting. And this is a somewhat personal matter, because sometimes when you try to reserve a meeting room and then you look at the schedule of the meeting room, then you see that no meeting rooms are available. And then you pass along that meeting room with glass walls so you can actually look inside. And then you see that the meeting room that you require is actually booked and there's nobody sitting inside, which is a very frustrating thing to happen. And the Colruyt Group, one of the partners in which we worked, they also had this problem. And they already tried to solve it. They actually made an application in which their floor plan is already showing each room, each meeting room, but also flex desk in which the colleagues work. And then they installed passively infrared sensors, as you can see to the right top, which can actually measure the activity that is happening inside a room. These sensors are unaware of, have no privacy issues, are fairly easy to install, and are very cheap. However, they require a level of movement. I've known in companies where they actually installed a script to do a printing of a page just to trigger the camera or the light sensor because it was unaware that people were still present, so it's a problem. It's only binary. We only have yes, there is activity, or no, there is no activity. So we also have no people count. So a meeting room which is capable of filling 20 people might be used for 2 people, which is also a problem which we maybe want to tackle. And the first thing, since this is a scene perception vision based, the idea was to place cameras. So why not place cameras which we can actually use to extract the locations of people or count the number of people present? But a classic camera, which you place typically at the corner of a room, well, at some distance, the people are very far away, are very small. As you can recall from my example, the babies hanging on the wall, the picture, they were often with lower confidences or they were missing. So people further away might cause a problem. And also in flex desk environments, monitors might occlude your presence or something, which might cause you to not be detected or counted. Instead, we actually propose to hang omnidirectional overhead cameras at the center of the tables or flex desk environments, which are capable of capturing a 360-degree field of view of the room. However, I don't know if you had the idea, not everybody likes to be recorded when they are working in their workplace. A camera which is in your face or the idea of being recorded is not always even pleasant. So indeed, we also wanted to fix that issue. Our goal here is to have embedded people counting on omnidirectional images, taking into account the privacy by reducing the image resolution while using temporal or time information to retain our accuracy or our performance, where we try to optimize the trade-off between performance and processing speed on embedded platforms. And we want to develop as well, as I will discuss later, a method to automatically annotate a training data set based on a problem that I will discuss now. So as I've stated before, models tend to be trained by example. And if you look at these models, then we have an immense requirement of data to have a generic data set and to have a generic model which is capable of doing a certain task. However, these images are very special opposed to a smartphone image, and therefore only a limited number of data sets is present publicly. And these have also very little scene variations, which means that they are very statically, always the same room with only people moving around. And we also have within these data sets different camera types, resolutions, and positions in which the camera is hanged. So building a general idea or a general technique which is generic is quite challenging here. Furthermore, we reduce the quality of our images to retain privacy, which causes us to even decrease the data even further on purpose, causing an even larger problem. Therefore, we already, to overcome this, recorded our own private office data set. However, this data set is unannotated. We don't have human annotations. And in future, when we want to train on more data, then we will also have that problem of having no annotations. So therefore, the first thing that we actually did to overcome this challenge of having a little bit or little to no data is actually to have a pipeline which is capable of producing annotations for us, so we don't have to do the manual work. Better be lazy. So for this, we actually made or followed a student-teacher approach, in which we actually use high-resolution images, which we unwarp into several images, looking more similar to the ones that we are already having today using our smartphones. Then we use certain object detectors and OpenPose to detect people on those high-resolution images. Then we use those detections and place them back on the omnidirectional images, and voila, we have our annotations, which we can use for training. When we look into more detail, the input you can see at the left. Then we unwarp it in certain pieces. We can, in this case, choose for 3 pieces. Then we run this algorithm, and then we get 3 detections on 3 images, which we have to combine, which causes some issues on overlap. And we can combine or warp them back using a point warp or just a bounding box warp. And then we have our annotations. And then in the next step, this data is used in a similar way as before. We clear away the last part of the YOLO V2 network using our own measurements. And then we can actually reduce or decrease the network resolution. Since we downscale our images, we can also downscale our network. However, we cannot go very low because of the network not working anymore at a certain point. To fix this or to overcome this, we also decrease the image resolution. And then we have an upscale, a linear upscale, to fit our network architecture. However, I told you that I was going to use temporal information to increase the performance. And we were thinking about, we can also replace linear upscaling by using temporal upscaling, using multiple images, low resolution images, divided in time or in different time moments, and combine them together to have a larger image. And in this example, you can see 4 types of kernels to the right, which we used in experiments to use this interlacing kernels as an upscale, a temporal upscale. And when we train several models using this approach, we can actually see that compared to linear upscaling, indeed our temporal information contributes to the performance. We get better results depending on the level of movement that is present inside of the room, because we presume that people are not static and are moving, causing the pixels to also show certain behavior inside of the images. And when we look at the visual output, we can indeed see that on the right images, these are the low resolution interlacing kernelly upscaled images. on which we detect the people, on which is, for me at least, impossible to recognize the people. And when we have the left images, they are used as a reference to actually prove that they are people walking around. And we can already see that it's working quite well. Here our contributions are that we are the first to propose such an approach for people counting from overhead cameras, taking into account the person's privacy. Well, we allow this network to run on small embedded devices, and we use low resolution images rendered impossible for people recognition. And we also propose our state-of-the-art self-training approach, which will use the higher resolution images to procure annotations for training. So we can actually train a model fairly easy. Our last use case is people-based 3D occupancy maps. And here we are situated in a 3D room or in a scanner room in a medical facility, a hospital or another room, where they have a robot, a robotic arm, which you can now see in the video, that is capable of moving around inside of that scanner room or image room to take X-rays of people, more flexible images and on more flexible positions with a single X-ray machine. However, people that are walking around inside of that room, medical staff or patients, they tend to walk around and the robot will, in some cases, have a collision with that person. If you are not aware of each other, then there can be a collision happening, which must at all costs be avoided, not only for the person's sake, but also for the robot's sake, because a collision is not good for either of them. And currently, a nurse is actually watching the situation with a switch in her hand, and her full-time job is assessing whether or not she should release the switch and freeze the robot of moving. And this is a very tiresome job again, but also if she loses her attention even for 1 minute and something happens, then that's not an ideal situation. So instead, they want to automate this by generating person-based 3D occupancy grids, which actually produce or generate a off-limit zone for the robot. So using detectors, we will actually measure or present a map of the room where a robot cannot move itself. And this means that a robot can never collide with a person if he is restricted of moving to a certain area. To do so, we have compared two single-shot detectors using multi-view images, and we have used a bounding box detector and an instant segmentation detector. And an approach that we followed is that we take several images, in this case 4 images around the room, and we will use a bounding box detector, detecting people inside of that room, and also an image segmentation network, which will also provide us with the contour of the person or the objects present inside of the room. We can add some dilation on the bounding boxes or the instant segmentations to provide some additional safety margins. And then using visual hull, we can actually depict whether or not a 3D position is occupied by a person from multiple views, and setting a threshold on the number of cameras that have to contribute to that pixel or voxel. We can actually set it as being occupied by a person or not. And we can also play with the threshold to which a detection must be reached or have reached. And when we look at the results, we can indeed see that the bounding box method has a more larger 3D occupancy grid compared to the instant segmentation grid, which is to be expected, since when we move our hands, the box gets drawn over them fully. And when we compare several PAR curves with minimal camera requirements, then we can see when we have a minimal requirement of 4, meaning that we need 4 cameras contributing to the voxels, we have the best precision, and we set the blue dotted line at a recall of 75% as a minimal that we need to have at least 75% of the voxels found. And we see that our YOLACT approach already has a precision of above 55%, which is already something. There is still room for some improvement, but we already proved that there is a feasible study here. Also, when we look at the time, calculating or detecting the people on 4 images simultaneously takes some time or more time than just on a single image, and we can see that it is acceptable within the 20 frames per second. So we need to count at 20 frames per second, which we reached. I think it's a mistake that I'm saying 5 frames per second, which we reached adequately. Our contributions here is that we are the first to propose an instant segmentation in combination with Visual Hull to generate real-time 3D occupancy maps. And we also compare 2 techniques to generate people-specific multi-view 3D maps with time constraints. And 1 publication was derived from this work. So these were the 4 use cases. And since this is an industrial application, or these were industrial applications, we also want to specify or highlight our valorization. Valorization means that we actually have used this technique in the industry itself. And for each use case, we can show this. The first is the autonomous cameraman, where we were in cooperation with Geronimo, a Belgian production house. And our work has actually allowed them to record 2 seasons, counting for 20 episodes with more than 620 viewers, 1,000 viewers, which is a lot. For our mobile eye tracking analysis, we were in cooperation with the UMC in Amsterdam, which caused 3 follow-up publications, so they are actually using our work, which is also very nice for both parties. Our privacy-aware people counting was in cooperation with the Colruyt Group, a Belgian group of many things, and they used this approach to optimize their workspace occupancy. And then we have the people-based 3D occupancy maps, which was in cooperation with Agfa, a manufacturer of X-ray machines, and this was more of a proof of concept study, which they will take along in their further research. The next thing I want to stress or want to show is the lessons that I learned, general lessons. I want to point out that a lot of lessons were learned, so I'm only going to go over 2 of them briefly. And the first is that my approach, and there is a missing link, my approach is that we, for the directing of the cameras, we use an open pose network to actually extract metadata, in this case the position of the people, and then we propose an approach to actually use this data to calculate a medium shot to be directed by the camera. However, often we see that in research fields, they just want to do end-to-end everything. They just want to make a network, they feed it some data, they tell it what to do, and they hope for the best. And I'm actually very skeptical about this approach or this trend of always trying to just have end-to-end learning. Of course, in some situations it's feasible, but I think you lose some control of what is happening. You're hoping that your canvas or your medium shot is good, but you cannot reason why it's not good. Whilst with my approach, when a person is not found and the medium shot is therefore not good or it's missing a person, you can reason, okay, the person was not found, causing my medium shot to be missing a person, which allows you for more reasoning and another intake on how to process or use these networks. So my preference goes to always looking at the first approach first. Can you creatively use existing techniques and just add certain components before you consider going to the end-to-end solution? At least that's my opinion or a lesson that I learned. The second lesson that I learned is concerning a video that I will be showing. And this is a person in his workplace with a non-privacy aware camera, which is slightly falling to the right. It's just at a certain point he's actually falling, and yeah, he was falling asleep of overwork or something. And what I want to show here is that, well, suppose we still have the traditional way of not having any computers doing any work, then this would be privacy breach and we would actually be invading this person's privacy. Whereas if we use a computer, then a computer is non-judgmental. He will just count the number of people and he will not be tasked to detect whether or not the people is actually doing work, which might already provide you with some privacy issues that are being resolved because there's no judgment from the algorithm that says, yeah, that person should be working instead. And here I want to stress that in some cases, cameras might, or techniques, artificial intelligence, might also improve the privacy opposed to just limiting the privacy. However, it must be guarded that it is specific to the use case. In certain use cases, it is possible. Lastly, I want to conclude my presentation by showing that I've used a person-based detectors, three types of person-based detectors, which I use to extract metadata. This metadata was used in 4 use cases. At least 2 of them was always used as in a comparison to extract a new type of metadata. This can be the medium shots, the privacy-aware people detections, the gaze matching to the regions, and the 3D map. And eventually we use this in an exploitation. We actually want to evaluate how well the performance of this output and this metadata is. And we showed that indeed it is already good at a certain point and we can already reach a certain precision. This is my final slide, which shows a quote by Zora Neale Hurston. "Research is formalized curiosity. It is poking and prying with a purpose." And with this quote, I want to ask my audience for questions.
Thank you. Thank you, Timothy, for your very nice, slightly too long presentation. Okay, ladies and gentlemen, the members of the jury will now have the opportunity to ask questions. There is an examination committee that has been appointed by the Faculty Doctoral Committee, and I will first introduce to you the different members of the jury. And I will be a little bit impolite. I will start with myself. My name is Maarten Vergouwen. I'm a professor in the Faculty of Engineering Technology of the KU Leuven. I am the chair of this PhD defense. Then we have Professor Toon Goedemee. He is the supervisor of this, the main supervisor of this PhD work. He is also a professor in the Faculty of Engineering Technology of the KU Leuven. We also have a co-supervisor, Dr. Christophe van Beek. He's a postdoc in the EVICE group of Professor Goedemee. Furthermore, we have one more person from the EVICE group, Professor Patrick van de Walle. He's also a professor in our faculty of the KU Leuven. We are also joined by a professor from another faculty, in fact another group, the Faculty of Arts, Professor Geert Brone. Dus de faculteit Letteren in Dutch. And he was also part of the supervisory committee during the scope of the PhD. We also have Dr. Wannes Meert, an IOF fellow of the computer science department of the KU Leuven. And we have 2 more people who have joined us remotely. I don't think we can show them. I don't know if we can show the cameras, but okay, never mind. We have Mr. Thibaut Rommens from Geronimo. We already saw the. I think you already mentioned Geronimo, right, in yes, one of the previous slides, right? Maybe just very briefly, the Faculty of Engineering Technology, we think it's very important, as Timothy already showed, that valorization is part of the research. And that means that in every examination committee there will be somebody from industry. In this case, it's Mr. Rommens who will be asking questions as a jury member. And finally, we have a professor from Denmark, Professor Rikke Gale from Aalborg University, who has joined us as well remotely because of the pandemic, obviously. The different people will be asking questions in the reverse order in which I introduced you. So we will start by Professor Gale, who will kick it off and ask questions. Please go ahead. I hope she could.
Yeah, there's a slight delay on
okay.
the live stream. So I hope she catches up.
She will have to turn on her microphone as well. Timothy, kan je anders even misschien in de chat vragen of ze ons gehoord heeft?
Oh. Ja, wacht. Maybe it's on our side.
Sorry, we cannot hear you.
Is dat bij jullie? Nee, hè? Ja, maar dat was niet bij de...
Ja, als het nodig is, haal ik mijn laptop en nemen we de andere cues. Misschien veiliger.
Ja.
Met de andere laptop.
Ik weet niet waar dat de audio uit... Of misschien staat er gewoon gemute. Ja, ik denk dat het misschien best is. Via HDMI of?
We zullen het gewoon zo doen, hè, als je het al kan horen wat ze vraagt.
Ja, ja.
Zo, kunt je haar vragen om naar de jury room te gaan?
Ja, normaal heb ik dat al gezegd. Normaal zijn ze onderweg.
Ja. Okay, Reke, can you say something so we can hear you now?
Yes, I'm trying to speak up. Yeah.
Perfect.
So I don't really see anything, but.
Yeah, but at least we can hear you, and I think that if Timothy speaks up, you will be able to hear him as well. I think that's probably the most important thing, right?
Alright, yeah, and I can see the picture from the live stream.
Oh, great. Okay.
Yeah, alright.
So please, you have the floor.
Yeah, it's a little bit difficult to hear you when you're far away from the computer, I believe, but.
You have the floor, Professor Gate.
So you hear me all right? Okay, I'll try to to start here. So first of all, thank you very much, Timothy, for a very interesting presentation. Yes, maybe it was a bit too long, but I think it covered some very interesting aspects, both genuinely about the introduction to computer vision, and also about all the work you have done. So nice work there.
Thank you.
So I have a few like general questions. So the first one would be, now you've been working with images and videos of humans. So I was wondering, lots of these CNN models are actually trained on humans. So how does it work now? Can you just take a pre-trained model that works out of the box, or do we have to do transfer learning or to add data from the particular domain? Well, what is your insight into this experience?
When you want to change your domain, when you want to detect other objects than people, is that your question?
No, so still working with people like you did, but obviously it has not been trained on your particular scene. But is it fine to use pre-trained data, or do you have to train it on the particular scene that you will be looking at?
I think the accuracy will actually improve if you have better data, generic data, which is not constrained to certain things. For example, a data set with only pedestrians will face certain difficulties when you transfer to a domain of in the household, where pedestrians are rarely seen, at least in a typical sense, and also the detections themselves. If you only have small detections, like in a pedestrian data set, then you cannot expect the model to suddenly detect larger or people who are larger visible in the scene. So indeed, it does influence it a bit. However, most data sets nowadays are very generic, at least the larger ones, which are used for training a lot of models. So you can at least have to or expect to have certain results already using these models. However, if your use case is specific to a certain domain, you might indeed need some transfer learning or some fine-tuning to increase the accuracy to your domain as well.
Mm-hmm. Yeah, okay. And of course, in one case you have this this overhead camera, which has a very wide field of view, so that looks a little bit different from most data sets.
Mm-hmm.
In that case, you also did something else. Okay. About the autonomous cameraman, so you said here as one of the final remarks that they actually did use that for some of the seasons of this reality TV. I was just wondering, based on the experience you have, will it ever kind of learn all the implicit rules about a good shot, or will it just be okay to reduce the data amount?
Both are feasible, but I think the main problem is the subjective field or the subjective nature of the project. So it's very dependent on whether or not a professional finds it good enough to be used in professional productions. I think for amateur productions, it will already provide some automation in maybe less important scenes. That was also their use case, that well, when we don't have anybody present 24/7, maybe we can run the algorithm on several cameras to have at least some better shots. If not, well, then that's a shame, but we can try it. But I would not fully replace it yet with autonomous techniques, at least not if you want to expect quality output.
Mm. But do you see that if you were to work on this for maybe one more year, would you actually see that the solution would be so good that you could replace the manual cameraman?
I don't think it will in a year, at least. It will improve, but I don't think we will reach the point where it's perfect. Mainly the reason there is the data. We cannot objectify the data very clearly. It's very difficult, so we have to use multiple shots and take the mean or an average of those shots as one eventual shot. I think we can already reach a certain level, but then again we will reach the level of the person who has annotated that data set. And that does not mean that another director or another cameraman will not have a different interpretation of how the shot should actually be. So I think that is a main challenge here. How can we objectify the data, or at least make sure that the preference of a certain director is not so, or that the model is not dependent fully on how well that dependence was. So I think we can certainly improve it, but with some certain limitations.
Yeah. Okay. Thank you. Then, especially one of your papers were about privacy privacy preserving methods. So can we talk about what are the general options for preserving privacy? One of them is obviously, as you did, to downscale the resolution so that you can't recognize anything. Are there other options that you could choose for this purpose?
Yes, so it depends on the legislation of the country. The government set rules, and in our country at least, we cannot transfer the data, we cannot save the data, we can process the data. So when you have an embedded device, for example, and you never leave that device on a network or etc., and you only output privacy insensitive data, for example, the number of people present, then you can speak of also a privacy preserved system. So you can use an embedded platform for calculations. That's one thing. And the other thing is that you can indeed reduce the resolution. And on the top of my head, I cannot think of a third one. So I think those are already the major ones to ensure the privacy. Maybe use a different type of camera, might already also provide you with, like using a thermal camera or something, might also provide some insights or some privacy.
Yeah, because the type of sensor could also influence whether we say that we have some personal recognizable features or whatever we record.
Mm-hmm.
Okay, let me just ask a final question here. So that is about the application where you use the eye tracking glasses.
Mm-hmm.
So you said that you had the best results where you use the pose estimation, where you find the key points in the face,
Mm-hmm.
and then estimate the area of interest based on that. I was just wondering, why not go with a segmentation approach? It looks like that's what you're actually looking for, the segmentation of the face.
Mm-hmm. That's actually a possible next step. So we would be interested in indeed using the segmentation in combination with another detection technique to actually have the area as well of the detected region. However, the research or the technique that I used in my last use case was not yet there, or at that point in time was not yet reaching the same accuracies and performances, so we didn't yet use it or compare it, but indeed that would be something worth testing out.
Okay. Yes, thank you. I think I'll pass on the word to the next jury member.
Okay, thank you, Professor Gate.
Okay, thank you very much, Professor Gay. Then I would like to ask Mr. Rommens to ask some questions. I don't know, Thibaut, if you can hear us.
Yes, I can hear you loud and clear.
Perfect, and we can hear you as well. So please go ahead, you have the floor.
Now, unfortunately, I was not able to follow the live stream of the Teams meeting of the public defense for some reason.
Okay. Now, normally there was a separate link on the that I sent to the jury where you can follow the presentation, and so maybe that was a mix-up in communication.
Tried that one as well, but I wasn't let in. I couldn't see anything.
Oh, okay. I hope that went okay then for the... We don't have visual feedback, so I hope at least some people then... My apologies for the technical difficulties.
Well, fortunately, I already asked a lot of questions on your first presentation, maybe a bit too much. So I would really like to ask a question that I couldn't get the answer to the last time. In your fourth chapter, it is in your final thesis, you use an interlacing kernel. If I read it correctly, you use 2x2 matrices to interlace different frames. Is that correct?
Yes.
Why exactly do you use 2x2 matrices?
Well, we downscaled the images to a resolution of 48 by 48, 36 by 36, or 32 by 32. And when we upscale using a 2x2 kernel, we actually double the resolution that we get at the end. And when you double the resolution of 48 by 48, you get that 96, which is the resolution, the lowest resolution which we reached for the network architecture. So at that point, that was a logical step to take that kernel as an upscaling method. But indeed, we could enlarge the interlacing kernel size to a 3 by 3, but that would result in a larger image. And then we might have the requirement to either enlarge our network architecture again, to have a larger network and have more computational power needs, leading it to run slower on embedded platforms. Or we have to downscale the image again, which might cause artifacts to occur. So that's why we did not bother to take a swing at it, to do the 3 by 3 kernel. But indeed, it would also be something we could test out.
So the trade-off between speed and accuracy was actually enough with the 2 by 2 kernel. You didn't have to go any higher.
No, indeed.
Okay. Yes, I believe that's all.
Okay. Thank you, Mr. Rollins.
Okay, very good. Thank you very much. I don't know if we will leave this stream on in case either of you would like to intervene again, maybe by the end of this of the defense. All right. So then we will move on to the people present here in the room, and I would like first to ask Dr. Meert to ask. I think I'm going to ask you first to ask a couple of questions, but I will move. Or Patrick? No, we'll ask. We'll ask you here first. I will give you the microphone.
Thank you, Timothy, for the very nice presentation. Visuals definitely helped to understand your cases. So you, in the presentation and throughout the text, you mentioned a few times that you looked at the trade-off between precision and recall, and then how you try to find the best value there. So I want to ask a few questions on how to get even, if it's possible to get even higher than just finding these best points or trying around. So first, you already mentioned that you can just have more data, more generic data, more diverse data, and your methods will improve.
Mm-hmm.
But on the other hand, if we look at a lot of real-world examples, take Uber, they have millions, even hundreds of millions, even more pictures, and still they miss that a pedestrian can cross anywhere.
Mm-hmm.
So a recent stream of research that we see coming up is verification of these models, like automatically finding edge cases, adversarial examples. So what's your vision as an expert on this, on these two streams? Would you say that you have another 5 years to work on this? Would you invest all your effort in this verification adversarial track and go into robust models? Or would you go into better data sets?
That's a fairly good question. Indeed, companies like Uber, Facebook, they have a lot of data. And I think at a certain point, the genericity, I don't know if that's an English word, is saturated and you don't have any more generic parameters that will actually make it better. In some cases, it will actually make or decrease your accuracy or your results. So indeed, data sets help to a certain point that I agree upon. And then verification or adversarial, it helps. I'm not really an expert on those two topics in particular, but the model or the influence of the model itself will also influence how well or not you will actually use it. And when you look at verifying whether or not a model is good or the data is good enough for training a model, will certainly help in increasing the performances. So I don't know if that's an adequate.
Yeah. I'd like to expand a bit on that, making it a bit more challenging even, because you correctly refer to the fact that you need this kind of like types of reasoning to improve the models, and then you had this nice lessons learned that you want to have these separate steps because you want to recognize the pose before you start making assumptions, and that end-to-end will be very difficult because you kind of want to capture this knowledge and then do something with it. But then in the learning, you showed like, I only cut off this last part, I'm gonna retrain the last part. isn't that a bit of a contradiction in your lessons learned, or is this something that you think it would even improve it further by going deeper into this network and maybe even having this kind of abstract knowledge that you could push into this network, or do you think that's just impossible? Let's keep it to gradients and propagate numbers.
I think everything is possible nowadays if you have the unique setting and the unique idea and possibilities. So I will not say that it is never possible. However, what I showed with cutting off the last layer, I was only trying to fine-tune a certain piece of that pipeline to detect a certain thing. However, you can indeed challenge, why don't you find just pieces and then combine it together to have the full pose. And you can abstract it even further or make it low level. And I think there's something to be said for both of them. Indeed, you can go and fine-tune multiple parameters, multiple layers using multiple data sets or multiple preferences. And I think that would certainly help, but I think the search for those parameters would then be, again, manual, or you will automate this. And at a certain point, how much time will you give this to optimize itself? And in these cases, which is also something that I learned but not said in the lessons learned, is that sometimes time is short and the industry wants to move on, which is also challenging because the industry pushes you to have results yesterday instead of tomorrow. So indeed, if you want to have the best model, you can spend more than 5 years even to fine-tune it and to get better results. And I'm sure that in 5 years, when I do the same research again, I would do certain things differently because the techniques have evolved and new approaches, like I've seen today already, will show themselves explaining that, well, when we do this trick, then we get better results, and we just have to find what to do. And within the scope of my research, I've not been tasked by doing the search for those things, unfortunately.
And then a last question about the neural nets that you've used. There is an explosion of different types of nets, and you focused on the convolutional ones. But then all the layers in between, there are so many choices. We've seen this move to attention, then papers that say attention is not necessary anymore, back to convolutional, back to pooling layers, not pooling layers. You've done all of this, or a lot of these things, so what would you advise as the next thing to focus on what type of network architecture, or do you think the ones that you've used, that's going to be the best direction?
If I could tell you which ones would be best, then I think most of the research would be obsolete, because then why would you research it? So maybe that's difficult, but I think the power of what I was doing, and also when I showed in my lessons learned, the open pose framework or the other frames that I used are just a piece of my puzzle, and I try to find what to use behind those pieces to get a good result. And this means that if you change to a newer technique, you indeed get different results, but maybe they don't vary that much because my technique simplifies certain things. So finding a person all the time or finding it a little bit better might not really have much influence on that medium shot that I was taking. So those pixel details are maybe not so useful. And when you think about the future and what way to, or what path to walk on, then I would say that a lot of research is being done compared, and I would just follow a bit the trend, but try to be creative and find something that matches your use case as well, because a lot of the things are, there used to be a trend when I started very early on, go deeper, 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 but they came back from that and they went the other direction, because at a certain point they don't achieve either better results or they have other limitations, like computational limitations, which they have to reconsider certain things. So I think it's an evolving world, an exciting world, and I think if you have to keep up, it's going to be difficult. So try to, in the industrial setting, choose something that seems worthwhile testing and try it out, and then you can see whether or not you already get the desired result. For at least my research, I did that approach a lot.
Okay, thank you.
Okay, Professor van der Wallen.
Thank you very much. Thank you also from my side for a nice presentation, Timothy. I'd like to start my questions with actually the first one of the lessons learned you mentioned. If I understood you correctly, you mentioned that you would prefer not to do an end-to-end deep learning approach and rather propose to split it up in a number of subtasks so that you can reason better about what comes out. Now, that made me wonder, doesn't that kind of also lead to taking this further and also taking, for example, your open pose or your person detector and splitting that up in a number of subtasks, and that allows you to reason about it, but it's maybe a bit against the current trend of applying data to do deep learning, and which also gave pretty good results. So can you comment on that?
It's a good question. In the past, they actually used that methodology. They actually detected manually hands, shoulders, etc., and then they combined them. And then when they didn't find a piece, then or they estimate it, or they just leave it out, and they could reason, we did not find that part, so we were unable to find a certain piece, and we didn't show it, or we don't show the full body because we need all the pieces to have a person. And in that, these are top-down techniques, and open pose is the different kind where you start from the bottom and you find each point individually and then you try to combine them. And indeed you could say, yeah, why not extract that and just have classifiers for each point, and then you can reason when you don't find a point. In this case, however, open pose is written in a way that it's obsolete to do so, because it will try to find the connections between them, which will contribute to the point being found, because when you have a path leading to the next joint, presuming that all people have all their limbs, then that will contribute to that point's location. If you were to extract that and do that separately, that might make it more difficult to combine the semantics of multiple things. So I think extracting too much components for reasoning purposes might also be negative. So I think we have to be careful not to extract too much or to reason or try to reason too much, depending on the use case. And in this case, it was a very good detector which was capable of helping each other by letting those pieces strain together. And I think if you pull them out again, that would not be the case. And that goes for many things. I think if you have a detector for each object instead of an object detector with multiple models, that might let you to reason, but maybe that gives you more challenges on other topics. So I don't know if that's an answer to your question.
Kind of, but then that would suggest that you can also, if you integrate the whole chain into your training, if you take the same reasoning, you would also be able to get better results by including all the steps into the training.
Depends on how you would train that, but indeed, I think it would be possible to do so. But then the human factor of deciding or having fail-safes even for when there is no person take a certain or hold a certain the time constraint or something might be difficult to get inside of that network. I think it's possible to make an end-to-end. I even know certain people who have an end-to-end solution. I'm just claiming or trying to say that it's not always, it should not be your first thought to train something end-to-end. And I think if you try to think outside of the box and use things that are already present and build upon of them, then you can still try to train end-to-end if that is not reaching your results, or if you try to improve them even further.
Okay. And then maybe to your last use case, which might not surprise you, the one about 3D. You mentioned in the people-based 3D occupancy maps, you designed a way to determine the free moving space for your medical device to move around. Now, here, I think you mentioned this with, let's say, one or few people in the room. How does this scale if you get more people in the room, or a more complex setup to configure?
Scale in the sense, will the robot still be able to move, or scale in the sense, will the algorithm still be capable of detecting it within the time frame?
I'm mostly concerned about the first, because I would hope that the algorithm, you can find a way to process it, but if the algorithm comes with the answer that the robot can never move, then we're also stuck.
Indeed, and I think that one of the constraints here is that we only have a cramped room, and I think if you pack it with people, then probably the robot would have a very challenging task of navigating itself throughout this space. Depends on how they implement it. They can also choose to have they can move it up and move it around using the upper levels of the room, or change those constraints, but indeed I think it will influence it greatly, which makes sense if you have a room full of people and you only have a resolution or a space with 1 centimeter of margin, then you don't want to see a robot passing just before your eyes. For me personally, that would not be comfortable.
Sure, but it might be, if you want to, let's say, extend this to larger rooms or manufacturing settings, how would you scale this? Let's say, if you have a large manufacturing space, it could also be interesting to make sure your robots don't interfere with the people present.
Mm-hmm.
But you might need to configure things differently than what you did now in your...
Mm-hmm. Mm-hmm. I think the resolution or the accuracy or the precision should be improved then you have better margins around the person as well, that you don't have blobs, but you have really the contours, which would allow more freedom without the risk of collision. So that's one thing. And the other thing is you can choose to either limit the movements by saying stop, but you can also say, let's change the speed of the robot, for example, and we can adjust the speed based on the approximation distance between the person and the robot, which might also improve the setting. And I would work in certain zones, something like that, where you combine the zones together with safe spaces where the robot can move freely, where people cannot move freely, and vice versa. And I think it would be best in large sites to have regions where both work together, where there is more security by the camera. But scaling up, it would be possible, but I think it's impractical in certain cases. I don't know if that's clear.
Okay, thank you. I'll pass the microphone.
Thank you. Timothy, I will join my colleagues in congratulating you on this very nice presentation today.
Thank you.
And what I particularly liked is that you mentioned during your presentation that apparently there are research groups interested in human interaction and real-life human communication. I happen to be one of those species. And I can reassure you that I was being the odd one out in this jury today. I was really able to follow your line of reasoning throughout your work and throughout the presentation. So that deserves congratulations as well. When looking at your dissertation, I think that each of the chapters is a coherent story in and of itself. And for me, it took some time to find coherence across the chapters, but then you have your chapter 7 with the lessons learned, where it all is brought together, and I think that's really neat. And I would like to try and ask some questions today that actually do the same, in the sense that you will not be surprised that I would start with chapter 5, the eye tracking chapter, and then ask questions on how maybe some of the insights from the other chapters could feed into that chapter as well, or the other way around. And my first question would be, you mentioned in your chapter 5 that one of the things that stands out in your work on the mobile eye tracking data is that you allow for recordings in authentic settings, unconstrained settings that are mobile in many ways. But at the same time, you could argue that the recordings that you've used in that chapter are relatively static in comparison to the other chapters in your dissertation. In the sense that these are static settings like the medical encounters with people sitting down and there's not that much in terms of movement going on, not that many artifacts. Now, what do you think will be the main challenges if you would apply this kind of technology to, for instance, the type of data that you have in your user case 1, where there's a lot of action going on at different levels? Because that is one of the things that this strange species like I am very much interested in this question of what happens when people are walking and talking. So could you maybe just elaborate on what you think are the main challenges in trying to explore this?
So the data in the first use case, the main challenge there was that we have even less constraints in households. So that means that one of the things that is important when you capture an image is the light. And in these cases, sometimes people tend to enjoy the darkness and just have a television flash inside of their faces. And for a camera, that looks really like a flashlight, which is directed. And in some cases, our detector fails because everything is black except for the white flash that goes on the person. So those were very challenging images in which our detector often failed, which was acceptable since people in that use case, people watching a television is very boring on a television because you are doing the same thing. But in the use case of trying to communicate, well, when you want to do mobile eye tracking, then you're always at the idea that you perceive as what a person is actually perceiving. So the data, when we try to project the type of data on the same situation where you are actually the wearer of a glasses, then I think the algorithm would indeed, we use the same algorithm. So in the medium shot 2.0, we actually used OpenPose as well, just because it really performs well. One of the things is that it's a semantic algorithm, so that means that if a part of your body is not present, it will try to match the other points or find the other points, which increases the recall, as I've shown in my results. And this is also the case in the household settings. So if you move a lot, if at least a certain part of the person is described, then that would be, we would find the people. On the other hand, there's also the false positives, where you find people who are actually not there. And that's also something that we saw inside of the presentation, or in the data set of the first one. In some cases, a poster or even a coat hanging on a chair was detected as a person. And these things cause more problems because they actually present you with annotations or detections which are false. However, in the case of mobile eye tracking, I wonder how long a person would actually look at a coat hanging there, and maybe that's also a nice subject to detect or to use in your research, Professor. So maybe that's not a disadvantage, but in this case maybe an advantage, but that I will leave aside. But I think that's something to consider. False positive rates is, I think, a major challenge composed to false negatives. I hope that gives an answer.
Sure. This, in a way, I think brings me to a second question that has to do with the comparison between human annotations and your algorithm analysis. Because there, I think you end your chapter, I wrote it down, in the future it would be interesting to investigate the exact frames where the manual analysis and the algorithm analysis differ. And I'm sure you have specific hypotheses based on what you've seen in your data. So is there any sort of systematicity in those differences?
Yes, but it's a difficult one to say because it's actually a hardware challenge. So most of the errors that were made were actually errors that the Tobii hardware produced. We also used, or the human annotators used software by the manufacturer, and we see the raw data differs from the data that was actually processed by the program, and we cannot break open software that costs many thousands of dollars or euros very easily. So it's very difficult to depict, are we doing the mistakes or is something happening wrong in the software? And those were actually the major issues, that the human annotator annotated correctly. Visually we checked that frame by frame and the annotations were correct. We saw a gaze not falling on the head, and the output was that it was falling on the head. And there we were amazed, how can this happen? Fortunately, it only happens just when a gaze is moving towards an object. So that means that there might be some delays because there's a synchronization between the glasses and the eye cameras or the gaze cameras, and maybe there's some causes. But it's a difficult thing to assess because we have limited, yeah.
Good. I know that it's an issue with the Tobii systems. But could adding temporal information here, could that help in solving some of these issues? Because what human annotators do is they take into account context. When annotating data, you look at what you've previously annotated and you make projections on what's to come next, basically. Would that be something that you could integrate into your system as well?
Depends on how complex that context is. If the context is, we typically watch for 5 seconds, then we might search for windows of 5-second saccades on certain objects. We can reuse the identity of the people because we also have those, or we try to extract those. So if that's a contextual attribute that you can use, yeah, of course. But if you want to combine interactions with objects or with long-term relations, people who have married couples or children, and these are more complex contextual things to take in account.
Okay, thank you.
No problem.
Okay, thank you. We have had all the external members of the jury, but we do have 2 supervisors. I don't know if any of them have a question. Yep, you would like to ask a question? Okay, there we go.
If there's still time left for
Sure, it's fine.
Timothy, first I'd like to thank you for the presentation, very nice, clear and graphical presentation. But also for all the work that we've done within eVice, all the different use cases were really very multidisciplinary and showed real valorization potential. Well, not only potential, but real valorization, so that's really nice to see. As a co-supervisor, of course, we had ample time for technical discussions, so I'm not going to ask a technical question, but more a question on the lessons learned part of your PhD. You said in the background and the beginning of the presentation that indeed we had these old techniques like ACF, ICF, DPM, and so on. And then we've seen 7-8 years ago the trend with deep learning. And indeed, your use cases showed that deep learning is capable of achieving almost anything, right? The accuracy is really amazing to see. So you actually showed that deep learning is capable of doing so many complex things. I would like to actually reverse the question and can you think about what are actually the limitations of deep learning? What can be done with it right now? What are the difficulties? And how did they affect our, what were the implications on your own use cases concerning this matter?
One of the things is that most of the deep learning is trained by example. Not every technique. There are techniques who have no examples and learn things nonetheless. And I think in some cases when you ask a model to do a certain task, it will perform or try to do its best and perform a certain accuracy. However, when you vary or when your class, for example, changes, then your model will also change in performance. And sometimes we train something, we evaluate something, and we hope that it works as we evaluate it, and then in real life you see that your results actually decrease, and sometimes over time it decreases even further, whereas the model hasn't changed, or maybe the data has changed, or the circumstances have changed. And that's something I think colleagues of or ex-colleagues of mine which will try to embed that continuous learning. That's also something relatively new, I think, which poses another set of challenges, of course. But I think that's something that we limit ourselves. And there are a lot of cases where you have contextual information, for example, very complex models. You can make it so complex, but you have to try to train it as well. And that's challenging in itself, to train something, to have at least certain performances. So these are certain limitations that I can come up with now.
Okay, thank you.
And I believe the big boss also has a question.
Thank you. Only one small, of course. Timothy, thank you very much for this very nice presentation again. Of course, it's all the four of them are very cool use cases, but the one I like the most is the first one, the cinematographic thing. Robotized cameras taking views of everything. And okay, you explained why you use separate object detectors and so forth to solve that problem. But yeah, also because of your next job is also maybe connected to this case, maybe also interesting to think of that a bit further. I was wondering, so actually there is a huge amount of training material available for how to make movies. There are lots of movies. Of course, you can directly download legally or illegally. But don't you think there is a possibility to learn from the masters in a way? And that's what you didn't do in your application. So can't you learn by let your algorithm look at existing video material of very important and good cinematographists? So that's a question. How would you do that, or is that feasible?
That's a good question, thank you. Indeed, we had that idea during the work. Can we not use the massive amount of movies present and series present today to teach it? However, in this use case, we want to direct the camera. So directing the camera to a certain shot, it means that we already take a new position. And the only thing, in my opinion, that you can actually learn from movies is whether or not a shot is acceptable. That and the time between taking certain shots and which type of shot you would be taking sequentially. Those are the things that you have as data in your movies, unlabeled data. And it varies a lot which style is being used. Real movie experts, which I do not claim to be, will have large discussions over styles inside of certain movies and even in franchises. And I think that complexity or that combination is something that we can try to do, but it's difficult. Also, we were working in a live setting, which is not to be underestimated. These movies are not in a live setting. Most of them are trained and tested, and then even after the camera director with years of experience sees the frame, he still adjusts that frame. And the only thing that we see is the purely fine-tuned content. And I think that's difficult to have that same process learned. Of course, we can try to use the quality of the shots from those data sets as something we can learn and we can use on the shots that we try to acquire. And that's something that I think that's feasible, which was not performed in the work, of course. But the actual steering is a separate problem in itself. Also, we used overview cameras of very low quality, which might also influence how the model would react to taking this low resolution image over an overview image in full HD. Maybe our network would learn, I want quality. So it's difficult we can try to emulate that and maybe have limitations in what he can depict as quality measurement, but it's challenging, but I think doable to use at least certain parts of it.
Thank you for sharing your thoughts about that.
Okay. I would like to give the opportunity to the people in the audience. Might there be anybody here who would like to ask a question or maybe formulate a thought, observation? Nobody? Don't be shy, it's okay. In that case, I would like to ask one more question. I'm just wondering whether you're not cheating a little bit. And what I mean is, when you're talking about the privacy app, you're downscaling your images, but then afterwards you're adding temporal information.
Mm-hmm.
Well, let's say that you would take some kind of super resolution algorithms or deconvolution algorithms, something like that. Wouldn't that just deliver you an image that has a higher resolution on which you might be able to recognize the people?
I doubt that, because you lack data and super resolution images are very good at trying to fill the gaps. And typically what you can see is that we have a certain edge and it will try to fine-tune that at a higher resolution, and it will try to fine-tune the contour of your face, but I don't think that would actually give the details, the actual details. It will try to match something, but it can go either way. So it will produce something, and when you take into account temporal information, it's all in the same limited data. So I don't add data, I add temporal data on the premises that people move, and furniture hopefully doesn't move. And that's what I try to embed, but I don't think that information will contribute to having suddenly, if you have 200 frames, that you suddenly have a higher resolution image. I doubt that highly. But prove me wrong.
I just might. Okay, thank you very much for your very clear answer. Okay, I just want to open it one more time. No. Okay. Oh.
Maybe there are questions from the online.
Yeah,
there might be.
Not,
I didn't
I'm
know.
not cheating. I'm looking at the platform, and there's
nobody there.
Nobody.
Okay.
There's
You're
only
absolutely
some.
right, Tone. I forgot about that. Okay, good. In that case, we will adjourn now. The jury will adjourn, and we will be back in a couple of minutes' time.